Well, welcome everybody, and this is webinar number 12 of our series. My name is Ian Mosley, and this webinar is going to be all about thermal design in power electronic systems. If you've joined our webinars before, then welcome back. If this is your first one, hopefully you find it useful. The format is that we have around about 1 hour's worth of presentation material here. This one might be a little bit shorter, followed by a Q&A session at the end. On the right-hand side of your screen, you should see a box where you'll see chat, questions, and polls. So under the chat box, you should be able to put any comments in there and questions you have about the sort of technical running of the webinar. And I'm pleased to say that Jose Gonzalez from Warwick University is joining us today. He's presented some of these webinars, but today he's going to be looking after the questions, polls, and chat section. So any issues on the technical side, please put them in the chat box, and Jose will hopefully deal with those. We'll also be doing the questions session at the end of the webinar. So type your questions into the question box and we'll pick up on those at the end and hopefully have a useful and interesting discussion. And we have a number of polls that we will launch throughout the webinar just to get a feeling of whether you're engaging with the material, whether you're finding it interesting, that sort of thing, really. All of the previous webinars we've done so far are available on demand. You can access those on our website. So let us know if you want to access those. You can get all of those free. I think that's probably it for the introduction. So we'll get straight into the content now. And let me just bring my screen up. Okay, there we go. So let's get started. So on the agenda today, I want to give a very brief background on thermal management. And this whole webinar today actually really is a rather high-level overview of the key aspects of that we need to think about for thermal management and some of the techniques we can use to manage the heat generation in power electronics specifically. I'd also spend a little bit of time talking about what can go wrong at the extremes of temperature in power electronic systems. And most people, you tend to think the extremes of temperature being everything getting too hot. You can actually get problems when things get too cold as well, or if you're constantly moving between those two extremes, you create a lot of problems for power electronics. So I'll briefly be discussing some of the things to watch out for there. Then, what do we do, or how can we manage thermal loading in our system, the different approaches we can use? So if you've been in power electronics sometime, you'll be familiar with this sort of stuff. So we're going to be talking about air cooling, liquid cooling, and some slightly more exotic techniques, things like heat pipes and 3D printed heat sinks as well. But they're all pretty much doing the same thing. It's just how they're doing it is slightly different. Then how do we actually, in the lab, go about quantifying the temperature of our system? And there's a number of ways of doing that, and each of those approaches has good points and bad points. And I really wanted to highlight some of the ways we go about quantifying temperature rise in our systems here. Then also modeling at the design stage. How can you go about modeling thermal behavior in your system? And as you move into bigger and higher power systems, that can become quite complex, and there are some great software tools which can start to help with that now. And lastly, the thermal management doesn't exist really as a tool in isolation or as an aspect in isolation of the rest of the converter design. Some of the decisions that you might make to manage the thermal design of your system may have trade-off and consequences for other aspects of system behavior, specifically EMI. And as you go up and up and up in power levels, some of those trade-offs become more strongly linked, if you like. So I wanted to discuss a couple of those just towards the end of the webinar, just to give a feeling of where this thermal management fits into the broader system design. And then we'll do a brief summary, and then we'll do our questions at the end. So firstly, our background on thermal design. This is not exactly rocket science, but I think it's fair to say that thermal management in power electronics is, and I think it always will be, the limiting factor in power electronics. And it doesn't matter what type of technologies we come up with, the latest high performance switches, for example, silicon carbide, gallium nitride, using high performance Litz wire in windings to increase the efficiency of magnetics. all that's really doing is increasing your efficiency in your system, and there'll never be a system that exists that doesn't generate any heat. So you always will have to deal with heat, especially as you're pushing at the limits of your power density in your system. And we've experienced this second point I've just put up ourselves, certainly firsthand here. So if you're lucky enough to play around with some of the latest generation technologies, you can really push the efficiency up to some very high levels now. And what you tend to find happens is each incremental improvement in efficiency that you achieve, actually you then get encouraged to put more power through the system, because it creates a higher power system, which has more value to the company you're developing this for. So even if you make something more efficient, you end up putting more power through it, and then you end up with the same thermal limited situation, just at a slightly different design point. Or if you make it more efficient, you can also make it smaller. But if you make it smaller, you end up then being thermally constrained. So again, whatever you do there, you end up running into this barrier of thermal design. So it's really important to understand how you can maximize your thermal design, because that really determines how good you can make your product. Both thermal management and efficiency drive power density. One thing to bear in mind, a lot of presentation material and information available focuses on power management in power electronics, specifically for power semiconductors and magnetics, because they're the parts that generate the most heat in the system. So people tend to focus on that. However, you've got to be careful that you don't forget everything else. There's multiple sources of heat generation in any electronic system, and including in a power converter. If you're using a digital processor, for example, that might be generating heat. If you're going up to higher switching frequencies, like an LLC converter, for example, might be running a few hundred kilohertz, you've got to watch out for the power level in your gate drive circuit. So that will generate heat itself. So you've got to be a little bit careful not to neglect everything else around your system, and make sure that the whole system as one entity is behaving well thermally. So the pure basics here. This is about as basic as I could make it here. So you have a heat source. It might be a transistor, resistor, LED, inductor, whatever it is, and you extract the heat to an external ambient, and I've put that in quotes here because what you decide the ambient is is really more to do with the perspective of the ambient from the heat source, and the ambient could be a number of different things. But ultimately, you've got a heat source that is transferring heat out to an external ambient sink. And to do that, you have a temperature gradient. So therefore, your heat source is going to get hot. You can model this. This is a Cower model, and if you joined us earlier this week, Jose's did an excellent presentation all about semiconductor packaging. And the Cower model, thermal model, is often used in semiconductor packaging to model the transient behavior of the junction of a semiconductor device as it dissipates heat, and that heat transfers out through the various layers of the package out to the external case, and then the heat sink and so on. But ultimately, I think the Cower model is quite a nice model, because you can use that to represent all aspects of your whole system thermal design. It's not, it's representing physical aspects in your system here. So if you take a look at it here, the Cower model is modeling thermal capacitance, which is essentially thermal mass in a system, and thermal resistance, and you get this transmission line effect. And that's important if you're doing things like transient overload conditions and things like that. You need to know what this Cower model looks like. So the key questions for thermal management, I think, are, firstly, how hot is it feasible to allow the components to become? And this is actually a really important point when I was putting this webinar together. What you consider to be ambient is a good question. Ambient is what I think it varies depending on the perspective of the component generating heat. And hopefully throughout the presentation, you'll see some examples that help to illustrate that a little bit better than what I'm doing here. But ambient is something that can change. The next point is, are we concerned about the transient thermal performance of our system or steady state? So again, we need to know what it is we're trying to model here and what we're trying to protect the components against. And what about applications where you've got multiple sources of heat dissipation? So you've got power transistors, you've got magnetics, you've got gate drive circuits. All of these feed heat at various different points into our, if you like, our system level Cower model, and therefore the temperature of or the heat generation of one component can influence the local ambient of another component. So it's difficult to look at one component in complete isolation of everything else in the system. And also, what does transient thermal performance really mean for different size components? You know, if you have a tiny little 0603 resistor, it has a very short or very small thermal capacitance. So, you know, it'll heat up very quickly, whereas a big heat sink might take minutes or tens of minutes to warm up. So you need to think about the time scales here between different parts of the systems when you're thinking about transient thermal performance. So briefly, what goes wrong at the extremes of temperature? This first slide, I had a bit of fun with this one because I thought I'd put it in here because we have experienced in some of our designs what can go wrong when a power circuit is actually too cold. And there's some interesting things that start to happen. So one of the big problems you get in passive components, at least, is if you have an electrolytic capacitor, the liquid electrolyte can freeze as you go down to low temperature, and the electrical consequences of that. This is a pretty nice part from Rubik on this one. Long life capacitor, 105 degrees C capable. But if you take a look here at -25 and -40 degrees C, compared to operation at 20 degrees C, you could have up to, depending on the voltage class, a 10 times increase in the impedance of that part down at those low temperatures. And that's a big problem because that means you're at low temperatures, the output ripple and the EMI levels in your converter could rise above to higher levels. Oops, gone too far there. And in the worst case, if you've not designed a robust control loop, your control loop could become unstable down at low temperature. So you need to quantify this sort of stuff and actually perform stability tests at low temperature as well. Resistors, I had a quick look at the standard sort of 1% tolerance resistors. These are pretty well behaved actually with temperature. If you look here, the 1% resistor example we've got here has about 100 ppm per degree C. And that means, degrees K here, that's about 0.01% per Kelvin. So they don't really shift that much actually, not in comparison to the capacitor here. Ceramic capacitors, depending on the grade of the ceramic material, can change massively, and you have to be really careful. And you can see certain ceramic capacitors are available that seem to have a hugely high energy density capability, but they tend to be the ones with this Wi-Fi V characteristic. And I wouldn't really advocate using that sort of a dielectric for power electronics, because look at the variation you get in capacitance over temperature for a Wi-Fi V. It's huge. If you need a really stable capacitor with temperature, then you need the COG type characteristic here, which has an almost flat characteristic. X5R takes you up to about 85 degrees C with a certain amount of change, and X7R is a little bit better than that. It goes up to 125. So the important thing is, again, for ceramic capacitors to look at the temperature behavior and make sure that those changes in capacitance are something your circuit can tolerate. Otherwise, you could have all sorts of problems there. On a mechanical side, I've seen this firsthand actually. If you have a liquid-cooled high-power converter system, down at low temperature, those liquid coolants that are flowing through the circuit can either become very viscous or they can actually freeze. And that creates a really obscure problem in that when you first power this up, if you first power up a high power converter with liquid coolant that's frozen, you can't get the liquid flow through the cold plate and out to the heat exchanger. So actually you can't, even though it's down at low temperature, you can't cool that power converter properly. So you could end up with a situation where the power converter quickly overheats because you can't, the liquid coolant isn't able to flow and extract heat properly. So you might need to sort of pre-warm the coolants then, just to make sure they're working and flowing properly. And that's something that, in particular, things like high power EV charging systems have to be careful about, because they're exposed to very extreme temperature changes. So low temperature can cause as many problems as high temperature here, and it's something that people don't often think about. Okay, so if you've worked in power electronics much before, you'll know all about the sort of things that can go wrong when you start running circuits and they get too hot. So this is a fairly normal example, really. An electrolytic capacitor, again, is a bit of a weak spot because it has that liquid electrolyte inside. So if you take that up to a high temperature, you create a pressure buildup in the case, which can cause, firstly, the electrolyte to leak out over time. So you get a permanent reduction in the capacitance and an increase in the ESR. And if the temperature gets too high, you can actually get the part venting, which obviously is a pretty much permanent and rapid degradation in the performance of that part. So you mustn't let electrolytics get too hot. You also have to be careful on the insulation in magnetic components. You know, if you've got an high frequency isolation transformer, the classification of the isolation material between primary and secondary is only good up to a certain temperature rating. So class F, for example, the maximum temperature you can have as a hot spot on the winding is 180 degrees C. So you've got to be careful that you don't exceed that, otherwise you can have a breakdown of insulation, which brings the obvious sort of hazards that you might imagine. Magnetic materials, if they get too hot, there's a thing called Curie temperature, and what Curie temperature really is the temperature above which the magnetic properties of that material disappear. So rather than having a nice ferrite core for your flyback converter, suddenly it appears like an air-cooled part, and the relative permeability drops down to almost zero. That will just cause your converter to fail. So you must keep the magnetic materials below that Curie temperature. You can, beyond a certain point, get thermal runaway as well. So for a typical MOSFET, the RDS on of that MOSFET will increase with temperature. Excuse me. And at a certain point, if your device gets hotter and the RDS on increases, the device will get a bit hotter. And then if that can carry on in an uncontrolled manner, obviously your device is just going to overheat and fail. So you have to be careful to avoid that sort of thermal runaway problem. There's all sorts of, I guess, electrochemical or electrophysical effects, I don't know the best way to describe it, most of which become or occur faster as you go up in temperature due to the Arrhenius relationship. This is an example of electromigration whereby you can get, under high current and temperature levels, you can get a migration of the metal material on PCB traces or metallization layers in semiconductors. Ultimately to the point where you get a breaking in that conductor. So you need to avoid high temperatures because they tend to cause these sorts of problems to occur much faster and ultimately cause reliability and lifetime issues. So high temperature, it has a massive impact on reliability, and we have a dedicated webinar on reliability coming up. But reliability is impacted negatively at high temperature. Lifetime is significantly reduced. You can, in some cases, get instant failure due to that thermal runaway situation, or maybe an electrolytic capacitor rupturing. And you could get safety being compromised. So high operating temperatures are bad for power electronics. Okay, I've mentioned low temperature and high temperature. If you joined us on the webinar earlier this week, Jose was talking about power cycling, whereby you're moving between those two extremes many times. And that creates a big problem because of different coefficients of thermal expansion causing mechanical stress. And a good example, and I think Jose talked about this on Tuesday, is when you get wire bond liftoff in semiconductor materials, the repeated thermal cycling just causes the stress to build up on that junction, and you get the wire bond lifting off, which obviously is going to be either a failure or a degradation in the performance of that semiconductor device. Also, ceramic capacitors can suffer problems here because they are a very hard material. If they're constantly subjected to mechanical stress and strain, they can ultimately crack, and that causes a rapid failure of that part. So you have to be careful about power cycling. That has a massive impact on system reliability and lifetime. So, approaches to thermal management. And again, this is not really rocket science. It's just the common approaches that you might be able to use to try and avoid some of the situations I've just described. So, forced air cooling. That's quite a neat thing to do. You're just blowing your cooling mechanism, your air, over all the components in your system, or if those components are bolted to a heatsink, the heatsink is acting really as a thermal transfer mechanism to transfer the heat out to an external surface, which can be cooled very effectively. So forced air cooling is quite a nice, easy way to keep components cool. It's generally fairly low cost because you just need a fan and a bit of design work to help steer the air where you need it to go. However, if you are using forced air cooling, fans are annoying. They make noise, and they're also a point of failure. You need to, at a certain point, the bearings will wear out, so you need to replace them over time. So fans help reliability on one hand by keeping components cool, but they can cause reliability problems themselves because they then wear out. So there's no free lunch here. It's always a bit of a trade-off. One big downside of fan cooling is that if the fan's blowing air constantly over the power electronic circuit, it can suck in all sorts of dirt and debris which may get deposited onto components. And if you bridge isolation barriers, or you create a bridge between high voltage connections on a component, obviously that's going to cause a failure and a reliability issue. So in those cases, conformal coating can help in those cases because it creates a physical barrier between the leads of the system and the contaminants coming in. And also, you might want to think about using air filters. The trouble with air filters is they then need to be serviced to make sure they're unblocked. Otherwise, you lose cooling capability. So there's all these different trade-offs with air cooling. It's probably the most commonly used approach to cooling power electronics, and it has some real advantages. But you have to be aware of the service required to keep the systems clean and working well. The great thing about fan cooling is it directly extracts the heat from that system into the local ambient air, and that's probably the best way you can just get heat out into local ambient. It's a nice way to do it. This is an example of a standard sort of a heat sink from this company, and you can see that you get a certain performance with passive cooling. As soon as you start blowing any sort of air over those fins, 2 meters per second here, your thermal improvements goes up by more than a factor of 2. So any sort of a opportunity to blow air over your system will massively improve your thermal handling capabilities. So liquid cooling, as we go up in power levels, this becomes important. So the important thing really about liquid cooling is it's actually just a transport mechanism. It doesn't dissipate the energy itself. It just gives you a way with very low thermal impedance to transport heat from one point to another, and that's actually quite important for high power systems. This is just an example cold plate that you might find commonly used for cooling larger power semiconductor modules. And I thought I'd put this up here along with some metrics on its performance, just to give you an idea of how effectively we can transport heat from one point to another. So in this case, we spoke a little bit at the start of this presentation about what does ambient really mean. Now, from the perspective of the components that are sat onto this heatsink, we could consider the ambient being the temperature of that metal plate, and that really is the temperature is the incoming liquid temperature that comes into this particular part. So that's what we mean by ambient from the perspective of the semiconductors being cooled here. For this particular part, it measures 57 millimeters by 305 millimeters, and if you look up the data with a flow rate of 7.6 liters per minute, we get a thermal impedance of, well, a fraction of a degree C per watt. It's a tiny level. And actually, to put some a slightly better way of expressing that, we could dump 500 watts of loss into that cool plate, and the semiconductors would only see a 2.5 degrees C rise above the incoming liquid temperature. So it's a way to extract a significant amount of heat from fairly densely packed power semiconductor parts or power electronic components, and remove that very efficiently to an external system. The only thing is that you still need something to get rid of that heat to the ultimate end ambient, and the ultimate end ambient really is going to be the air that this system is sitting in. So this liquid cooling circuit, it will extract the heat and it will take that out to an external heat exchanger, and an external heat exchanger is nothing really more than a big fan-cooled heatsink, which is then extracting the heat from the liquid and just sending it out to the air. So you still need to build in, if you're looking at power density, you can't ignore the fact that you need to have this fan-cooled heatsink or this heat exchanger system somewhere else in your product to actually deal with the real heat. So liquid cooling is great, but just bear in mind, all it really is doing is providing a very effective way to transfer heat from one specific place to another. It's, for obvious reasons, it's used in increasing the power density of those semiconductor assemblies for very high power systems. One other interesting application I thought I would put up here is liquid cooling is also being used in other places where you need to remove a lot of heat from a very sort of focused area and extract it to another heat exchanger. For very high power rapid charging, DC rapid charging for electric vehicles, this is an example of a CCS2 cable that are available now in liquid cooled variants. And with that liquid cooling there, or about maybe a better way to express it is, without liquid cooling there, if you were to try and put 500 amps at 1,000 volts, so 500 kilowatts through that cable, you probably wouldn't be able to lift it up, because the amount of copper you'd have to put in there to deal with that power flow or that current without overheating would just be too heavy. So what the liquid cooling does here is it allows us to reduce the amount of copper. So we start to increase the dissipation in the cable, but the liquid cooling then extracts that heat away. So we can have a very high power DC rapid charging cable that we can still pick up. So that's starting to gain popularity now for much higher powered EV charging systems. 3D printed heat sinks. This is something that only appeared really on our radar in the last year or so, really. And this is quite a neat idea. So with 3D printing, obviously you can create all sorts of custom shapes quite quickly, far more easily than you can with a normal traditional planar type cooling plate. So this is an example of a double-sided TO247, and the manufacturers claim that using that with the appropriate amount of liquid flow, we can get 360 watts of cooling from that package, which is pretty amazing. We haven't actually tested that yet. I think I'd quite enjoy testing that and seeing what performance we can get. But you can extend that then to maybe 4 TO247 devices with slightly under half that power capability. Slightly under double that power capability, or even more. So I think the thing is, I would love to test that and see how well that performs. But I think this is a really neat idea if you're trying to use more traditional through-hole power semiconductors like a TO247, but you need to extract a lot of heat from them, and it's difficult to bend those over and bolt them to a liquid-cooled heatsink, for example. This is quite a neat way to do it. The other thing you can do is with 3D printing, the complexity of the shape is not really an issue because it's just a 3D printed part. So you can get more complex shapes and thinner profiles as well. And these are some examples that we found on the website. And I'll show this particular one here where my mouse pointer is. This particular one here allows you to embed a 3D printed water-cooled heatsink in the layers of a PCB, which is quite an attractive thing to do if you're trying to deal with a lot of dissipation with a PCB mounted component. And this is what it looks like. So this particular one here, it's about 0.8 millimeters thick, and it can be embedded within the structure of a PCB here. You have to obviously put on the inlet and outlet parts here, but they are available. You can do that. The interesting thing is when you look at the performance level that they claim that you can achieve with this. So this measurement shown here was with a system dissipating 96 watts of loss, and then they turned the water cooling on through this particular part, and you can see that the temperature in the middle here of the component went from about 77 degrees C down to 28 degrees C very quickly. Now, obviously, we want to verify that in practice, but I thought I'd include that in this presentation because I think it's quite a neat, fairly recent technology which allows us to have more flexible ways to think about extracting heat from all sorts of different sort of shaped components, including magnetics potentially as well. Okay, the last one on thermal management approaches are heat pipes. So a heat pipe is essentially a bit like that liquid cooled approach I've just described to you, except it doesn't require a pump or anything like that to operate. The way a heat pipe works is it has this structure which at the hot end we have this pipe with a liquid inside it. So at the hot end, the heat causes the liquid to evaporate, and then the heat, the liquid vapor then moves down the center of the channel, and then it condenses down at the cold end of the heat pipe back into a liquid, and then the liquid is then returned and wicks back around the external periphery of the heat pipe. And that's quite neat. It gives you a very effective way of moving a fair amount of heat from one point to another point on a board. It doesn't actually dissipate much heat by itself. In fact, very little heat by itself. It's just a very efficient heat transfer mechanism. So that's quite interesting in power electronics. There are different types of heat pipes available. You have to make, if your power electronics can be moved on all sorts of different angles, you need to make sure that you get a type of heat pipe which allows vertical operation. Not all of them do that, and it's to do with, ultimately, it's to do with how how this surface that transports the liquid back to the hot end is constructed. And there's some details here, a little bit of details about that. But if you need this to work vertically, you need more of a sort of I think it's like a sintered approach actually, that gives you lots of micro pores that allow the liquid to flow back round the outside. Where this is very traditionally or very commonly used traditionally is on laptops, where you're trying to make the laptop smaller and smaller and smaller, so very high power density potentially, but you've got a processor inside, and you need to extract the heat from that processor and move it to a fan that would sit somewhere towards the back of your laptop. So heat pipes are a great way to do that, and you can see that that's where they're very commonly used. So they're just a very effective transport mechanism to move heat from one part of a system to another where it can actually be dealt with. But that means they're also perfect for power electronics if you need that sort of capability. The good thing also is that if you use them correctly, you don't need any maintenance for that heat pipe. It's a self-contained item that just doesn't need any servicing at all, because there's nothing that really can go wrong with them. The only thing you do have to be careful of is that you don't exceed their temperature rating, because if you imagine what's going on here at the hot end of the heat pipe, we've got liquid that's evaporating, so we're going to get a pressure buildup. So if we make that pressure buildup too high, then there's potentially your fluid could leak out of the heat pipe over time, and it will lose its effectiveness. Or in the worst case, if it gets too hot, it could actually deform or explode. So you mustn't use them above their rated capability. Cooling magnetics. This is a pain. Everybody, or a lot of people, focus on how you cool semiconductors effectively for obvious reasons, because they're generating potentially a lot of heat. So there are some good solutions out there for cooling power semiconductors. However, magnetics are slightly more complex to cool. One neat thing that we've seen that can be done, especially for much higher power magnetic components, is you can enclose the transformer in a sort of a metal jacket, if you like. And that metal jacket really is just a very low thermal impedance to allow heat to transfer, say, from the external ferrite, the surface of the ferrite, out to another heatsink. However, one word of warning: if you're making up your own custom sort of a metal jacket for your magnetic component, you have to keep that metalwork away from air gaps in the transformer because of fringing fields. Fringing fields, if they exist near any conductive, electrically conductive material, will cause eddy current losses to build up, and you'll get it's almost essentially it's induction heating. Your metal heatsink will become induction heated by the fringing fields. And I've put up an example as of a traditional sort of an ETD, or I think it's maybe it's an EFD, I can't remember now, but a typical sort of low power ferrite transformer here with clips. And there's a reason the manufacturers put the clips on these longer edges here, because the metal clip is away from where any air gap might be formed in the middle. If they had the clips on the outer side here and there's an air gap in the middle, you would start putting significant dissipation into that metal clip. So cooling magnetics like this with metal jackets can be very effective, but be very, very careful with air gap positioning. The other thing to mention is for very high power levels, you can get Litz wire, which has a cooling channel built in the middle. We've not actually experimented with that ourselves yet, but I thought I'd put it up there for very high power levels. It allows you to get the benefits of liquid cooling right into the heart of the transformer, which is something that I think could be potentially very, very useful for shrinking that transformer down. Right, so moving on to thermal measurement techniques. How do we go about measuring our physical prototype on the bench? So again, this is not rocket science. Thermocouples, this is something that we use all the time, and thermocouples are great. They can be tied to components. They're very robust sort of a way to measure temperature. So they're very good for measuring individual component temperatures, which is great. You can also sit your device under test inside a thermal chamber and run the thermocouples in, so you're able to perform testing at all sorts of different ambient temperatures, and it doesn't really matter for the thermocouples. They just do their job, so that's great. You can do long-term measurements across multiple channels just using a data logger. So we have data loggers here where you might have 20 different thermocouple channels, and it just scans every 10 seconds. And this is an example of an Apple USB charger we played around with a few years ago, where we're monitoring 6 different channels, including the ambient. So the 2 input electrolytic caps, the main power transformer, and then the 2 output caps, and then the ambient. So it's great. You can get a build up over a long period of time of the behavior of your device. So that's fantastic. It looks like it's doing everything we need it to do. The results are generally very accurate as well, or one of the most accurate ways of doing this sort of measurement. But you do have to be careful if you're putting those thermocouples in a noisy environment. They are electrically conductive, and therefore they can pick up noise. So you have to be a little bit careful of noise. And also, one of the big warnings about thermocouples, if you're doing mains level voltages or even higher voltage systems, be careful where you put thermocouples, because they are physically electrical connections. If they touch any high voltage components, then depending on your measurement equipment, you could be exposing your measurement equipment to hazardous voltages. So there are safety issues on using thermocouples with high voltage components. Be careful with that. The other thing that you have to be careful with thermocouples are they're not particularly good at measuring the temperature of very, very small components unless you use a very fine thermocouple. And the reason is that the thermocouple wire itself acts as a very small heat sink. So if you were to take your thermocouple, like I've shown in the image here, and try and glue it onto the top of an 0603 resistor, all you're doing is sucking heat out of that 0603 resistor, so you completely distort the measurement. So you can't really use them for small components like this. So what do you do if you want to look at small components, or you're more interested in the system level behavior? Well, that's when you start using infrared thermography, and we use this sort of a camera here for this sort of analysis. That same Apple USB charger we ran under the thermal camera here, and you can see the sort of thermal profiles quite nicely here. The great thing about a thermal camera approach like this is that you end up you can monitor the whole system, that whole power converter, not just the components we expect to get hot. And that's actually a really, really important point. Now, when you're using the thermocouple approach I described in the previous slide, you've got a limited number of thermocouples typically, and you're only going to think about using them on components you expect to get hot. And you'll measure the temperature, and that's fine. The problem is if a component in your system has been badly designed and you don't expect it to get hot, then you're not going to necessarily monitor it with a thermocouple, and therefore it could get through to production with a thermal issue. Whereas if you use thermography as well, excuse me, if you use thermography as well, it'll show up any little tiny hot spots of components that are getting hot that you've maybe overlooked. So it's a great sanity check for a system, because, you know, the failure of an 0603 or an 0805 snubber resistor might cause a chain of events further down the line which cause your converter to fail. So it's important to understand the behavior of the thermal behavior of your whole system, and that's what IR thermography can do. You can also capture short-term transient events probably more easily than if you've got multiplex thermocouples, then your data acquisition system is switching between those channels, and it can only do that so quickly. With a thermal camera, essentially, it depends on the resolution it's got, but you can simultaneously measure many points very, very quickly, and therefore monitor transient thermal events very, very easily. So it's great for that sort of short-term transient event capture. You can also quickly quantify the local environment the device is operating in, which again is another way to think about and monitor what the real ambient condition is here. The things you have to be careful of with thermography, though, is it's not perfect. No measurement technique ever is. The problems you get with thermography is a phenomenon called emissivity, and it's a bit like the thermal reflectivity or I can't even think of the word. It's how thermally reflective a material is. So ideally, you want a system that is completely black and not shiny. And in that case, the emissivity doesn't really cause a problem. I'll show you some plots in a minute where we actually can see the problems that if you don't take emissivity into account, you can get erroneous readings coming through from a thermal image. And you can also get local heat reflections and other things coming in. So you've got to be a little bit careful with how you use this technology. And the other problem with thermography is you can't really put your thermal, at least I wouldn't want to put our thermal camera in the thermal chamber because you'd probably kill it. So unless you have a thermal chamber with an infrared transparent port built into it, you can't really use thermography for systems when you're doing elevated temperature testing. You can get thermal chambers with those IR ports in them, but they are quite expensive. So let's take a bit of a look at an example of this little 18-watt flyback converter. And what I've done here, if you look at the images, I've not painted. Normally what you'd have to do here is paint this whole system black, spray it black, a nice matte black color, and then the emissivity problem goes away. I haven't done that here because I want to show the difference. So these are the two output caps. This is actually a plus and minus 15-volt output. And these are the two main bulk caps on the output of that flyback converter. The top of one of those I've covered with like a black piece of matte insulation tape, and the other top I've left quite shiny. Now this video here, I've run this up to rated power, and I've sped this. I'll play this video in a moment. I've sped it up by a factor of about 20, so you can see the transient thermal behavior more easily in this example. And let's take a look at the difference in temperature between these two components. So this is the system turning on, and this is the great thing about thermography. You can see here, hopefully you can see it on your screens, at at the bottom of the screen here, these are little markers that I've put on various different components around the circuit, and they are a bit like a virtual thermocouple. They're just recording the temperature at those particular points over time. And interestingly here, on this particular system, it's actually the primary side snubber resistor. So, sorry, the primary side current sense resistor on the flyback. So this component here, where my mouse is this primary side sense resistor. And that's the part that's getting the hottest here in our system. So you can see as time goes on. Now, there are a few little, actually, if I can stop it, hang on, if I can stop it there. No, I can't stop it. There are a few things we did on this video that meant I was walking past this particular board, which made the camera move a bit. So that was actually affecting the position of the thermocouple. That's why we've got, or the position of the thermal point here. That's why we've got these disturbances here. And as the video goes on, we've then put a fan on and other things to cool it down. But I won't let the video run just because it'll take a little time. If we then let that get to steady state, so this is running after a fair amount of time, and I zoom in on the thermal plot, look at the difference in temperature. These two components are at the same temperature, the two capacitors. They're being subjected to the same current stresses. So you can see the one at the bottom with the tape on, with a nice matte black finish, that's giving us a temperature of about 41 degrees C, which is about right for this sort of converter. Look at the one at the top, the emissivity, because we've got such a shiny surface here on the top of the metal can, it reports a completely different temperature. We've got just over 26 degrees C here, and that we know that they're at the same temperature. So the error in the emissivity, particularly on shiny surfaces like this, in this case causes about a 15 degrees C difference in reported temperature. So if you are using thermography like this, be very, very careful. Either paint your whole circuit a nice matte black color to get around this problem, or be very wary of any sort of a metallic surface like this. You can see the same problem on the tops of these other secondary side post LC filter capacitors here. They're showing a similar problem. The legs of the output rectifiers here are quite shiny, so they're showing the same problem as well. So watch out for shiny surfaces with this approach. So in terms of modeling thermal behavior, we're getting towards the end of the presentation now. There's all sorts of ways you can do that. In the simplest form, if you're just looking at one physical component, like a semiconductor package on a heatsink, it's quite a simple thing to do. You know what the temperature of the heatsink is, you know how much power you're putting through, and you know what the thermal impedance is. However, you might have, in a real power converter, multiple sources of loss. And this is an example of a simulation environment called Plex, which we use for power electronics simulation. And the good thing about Plex is it's a multi-physics tool. It allows you to do thermal simulation at the same time as electrical simulation. So the way we do thermal simulation in Plex is this is one of the examples that you can get from Plex. You can put a heatsink around components. So this heatsink drawn here means that diodes D1, D2, D3, and D4 are all thermally connected to that heatsink. And similarly, we have another heatsink where we've got this is a PFC converter. So we've got the boost FET and the boost diode. They're sat on another heatsink. And these are actually coupled together. So these are technically the same heatsink. You then have a thermal impedance to an ambient. So what we're saying here is, in this simulation case, we have a 5 degrees C per watt heatsink, and the local ambient is 25 degrees C. We've also, you can specify the thermal capacitance, effectively the thermal mass of that heatsink. And in the simulation case here, that's 45 joules per Kelvin in terms of thermal capacitance. So it'll take a while for that. What it really means is it takes a while for that heatsink to warm up. This particular example is a 300 watt PFC system. I'm going to show you the simulation results in a minute. The simulation's running from an 85 volts RMS input, developing a 400 volt output. So a standard sort of single phase PFC. So during the simulation, these are the electrical outputs at the top. This is the mains current. So as we begin to ramp the output voltage to 400 volts, ramps up towards its rated 400 volt level. we start to see, as you'd expect, the primary, the input side mains current growing, which makes sense. And the reason I chose this particular example is it's got a nice 100 hertz variation over time. And that is interesting, because then when you start looking at the different time constants in the system, they respond in a different way. So let's take a look. This at the bottom here is the junction temperature in red of diode D5. And because D5 is handling essentially power flow at twice line frequency, so I think it's 100 hertz here on this particular example, we see 100. We see the junction temperature of that particular diode varying at roughly 100 hertz. And the reason it's doing that is because it's got thermal impedance, and there's a Cower model all the way out to the external heatsink. What we're seeing on the external heatsink here, the one at the bottom, the thermal heatsink, so the temperature of the heatsink that D5 sits on is quite a physically large heatsink, and it starts at 25 degrees C. And over 0.4 of a second, it's only risen by a tiny fraction of a degree C. So the heatsink time constant is massively longer than the 100 hertz massively longer than the 100 hertz that we're seeing here. So the output heatsink, or the heatsink that the diode's on, just responds to the average power really that's being delivered to it, or that's what you can see. If we go into Plex, you can actually specify for the MOSFET here a Cower model, and we did that. We went to the so where my mouse is now, this is the data sheet for that Infineon MOSFET, and actually it's a 6-stage Cower model. So you can have it's a network of resistors and capacitors that model the transmission line of heat from the physical junction of that component all the way out to the case. And we can map those straight into Plex here. So that's great. We can start to model more accurately what's going on in this particular junction temperature, if that's what we're looking to control. So if I now take a look at the actual performance of the heatsink temperature over time here, it's a bit of a zoom in this just to make it a little bit clearer. The first thing to state is that the junction temperature, obviously it has its own thermal impedance from the junction out to the case, and that's quite a low thermal impedance. So a certain level of power dissipation will cause a temperature rise above the heatsink transiently. And then pretty much that temperature rise is fixed, and then the junction temperature over a longer term just follows the gradual rise of the heatsink temperature. So again, it comes back down to time constants and what the local ambient really is. Now, for those observant of you here, we can discuss this a little bit more in the questions section at the end. There's when I was putting these slides together, I saw a really weird effect, and I couldn't work out initially why this was happening. Initially, I saw the heatsink temperature dip, and it doesn't make any sense for that to happen. What I have done here, though, for this particular simulation, to make the temperature of the heatsink change more quickly, I reduced that thermal capacitance by a factor of 100. So I made it far more quick to respond to heat being put into it. And it took a bit of looking to work out what was going on here. But when you actually dig in to how Plex forms this thermal model, and then you look under that mask, if you like, this is how it does it. So it models firstly the standard sort of junction of that MOSFET, and then it runs it through the transmission line that you've just defined. And when you look at the particular thermal parameters of that MOSFET junction, what I found, and that's this box here, is the initial temperature of that junction was 0 degrees C, whereas the heatsink was at 25. So actually what's happening here, and it's a quirky thing, and it wouldn't happen in practice because this is a bit of an abstract example, but what actually happened here is because I'd reduced the thermal capacitance of that heatsink so dramatically, it brought the thermal capacitance of the heatsink fairly, or within an order of magnitude of the thermal capacitance of the Cower model of the semiconductor device here. So what happened is that transiently for a very short time, that the 0 degrees C stored in the thermal capacitance of that junction temporarily sucked heat out of the 25 degrees C heatsink as that junction came up to the 25 degrees C point, and then everything carries on as normal. So if I'd have put an initial temperature here of 25 degrees C for that model of that part buried in the mask here, we'd have seen a much more expected behavior. But I thought I'd flag that up because it does show you've got to be careful with simulation, because you never quite know what assumptions have been made when people are putting models together. And those sorts of effects, a drop in temperature is something you just don't normally see in the real world. So it's important to try and understand and explain why we got that. So finally, we're moving towards the end now. It is possible to use finite element tools to do thermal analysis. They can be a very powerful technique. In our magnetics webinar that we did a couple of weeks back, we used a tool called FEMM to do the magnetic circuit design use and modeling the magnetic flux densities. That same tool can be used to perform 2D analysis of heat flow in systems. So it's actually a free tool, and we haven't actually used it for heat flow modeling yet, but I might take a look at it because it looks quite powerful as a way just to give you a bit more perspective on heat flow in systems. If you really get into detailed FEA analysis, particularly maybe of modeling transformers, you need to start using 3D tools. And this is an example of a commercial tool from ANSYS that allows you to perform those sorts of simulations. In this case here, it's just an example of a heat sink, probably a processor heat sink. So you can see the temperature distribution. Those tools can be very powerful. You can monitor flow coming through that surface as well to look at the cooling capability when you start blowing air. So we haven't got any more details on that here today. It's just I wanted to flag those up as potential tools that might be useful for particularly magnetics design, where you've got complex structures that all of which different parts are contributing to heat loss. It might be quite an interesting approach to modeling those techniques, those types of components. Very briefly, we'll finish up now with some system level trade-offs. I mentioned at the start that there are some system level trade-offs. You can't really look at thermal design in complete isolation of the rest of the system, especially as you go up in high power levels. So often what you'll find at high power levels is there's a conflict between the needs of good thermal management and particularly good EMI. And the reason for that is that to get good thermal performance, you need to couple very closely with low thermal impedance the source of your heat to a heat sink. And to do that really what that means is you want to have them very close to one another. Now that's great for meeting the requirements of thermal performance. However, that's a disaster potentially for EMI. And this slide, well, we've got a couple of images here. So the top one here is a high power 3-phase system where we've got some semiconductor modules. So if you look at the cooling plate on the bottom there, that's going to do a fantastic job of cooling those power semiconductors. However, in those power semiconductor modules, you've got devices moving up and down at high frequency. So all of those are sitting very close for good thermal reason to that cooling plate. And therefore, we're going to be injecting a lot of capacitively coupled noise onto that cooling plate. Now, if that cooling plate is earthed, really what you're doing is pumping a load of high frequency common mode noise into earth, which is an EMI disaster. So you can see why in that application, we've got a conflict between thermal design and EMI. And a slightly lower power example here, this is a circuit that you might see in a mains power converter. So you've got an input main supply, you've got some sort of EMI filter here, you've got your power converter stage, or sorry, rectifier stage, and then you've got the primary of, say, a flyback converter. And you've got a primary switching device. It's a BJT here, but it might be a MOSFET as well. And that's thermally coupled to this heatsink. So this you create a capacitance between this switching node here, which is moving at high frequency. You've got a reasonable sized capacitor here, which is again pumping current onto that heatsink. And that heatsink depending on where you ground it, can create problems. If you directly connect that heatsink to earth, this is essentially a short circuit. You're doing exactly what I described in the previous example. You're pumping a huge amount of common mode noise directly onto earth, which causes you an EMI headache. For some systems, what you can actually do is you want to create a short circuit path. You can't really avoid putting power devices on heat sinks because you've got to cool them. But what you can do is if you either AC couple that heat sink back to the local switch, or the local device, the local power circuit, with a capacitor that's big enough, or even perhaps a direct short circuit from that, or a direct connection from that heat sink to the local return here, that provides a low impedance path for those currents to flow back to where their source is, rather than flowing out into earth and causing EMI problems. The only problem, if you do that, say you create a direct electrical connection from the heatsink to here, it means that heatsink is sitting at live potential, which is a safety problem. So then you have to be careful to manage that. The good thing about a forced airflow system, so say you had this mains power supply where you had connected that heatsink directly back to the return here for low EMI, if you sit that inside an enclosure where no one can touch it and then just blow airflow through it, the air can still effectively suck the heat off that heatsink, but you don't have this ability. Nobody can physically touch that heatsink, so you're safe. If you didn't have forced airflow, you would have to sit that heatsink somehow on the external surface of your product, which means then that you have a safety problem. So really, what we're saying here is that the conflict between, or the good thermal design is in conflict with good EMI and safety at the same time. That you have to try and balance all of those things at the same time to make your system work well. So it's never, you can never just think about one area in isolation. So briefly to summarize, we're just coming up to the hour. Good thermal design, as we saw in the earlier slides of this presentation, is absolutely essential for product reliability and long lifetime. You've got to manage your thermal situation. As those power levels increase, what you tend to find is that the power converter design, it increasingly becomes a thermal and mechanically constrained exercise, because you have to deal with the increasing thermal challenge. So you become as much a mechanical engineer, or require mechanical engineering skills as much as electrical design skills as you go up in power level. Most power converters are systems which have multiple sources of heat generation, and I quite like to think that they all have from their perspective, looking out into the system, they all have their own definition of what their local ambient is, and it's important to understand what that is for those particular different sources, because it can affect their individual reliability and lifetime. The Cower model traditionally is used in power semiconductor modeling, but I think it's a very, very useful technique, because it really relates to the physical elements of heat transfer, which can be extended then to the whole system of components in your power converter. And the key thing then is to understand the various thermal impedances and thermal capacitances involved in that system. And lastly, one interesting thing about thermal design, with that sort of Cower model approach in mind, is that the time constants that you might be dealing with in your thermal design vary over a huge number of orders of magnitude. So for a semiconductor junction, remember some of the Cower model I showed you earlier in this presentation, some aspects of that Cower model have time constants of literally a few microseconds, because they're so tiny. But then as you go all the way out through the system to your large external heatsink, you might have a heatsink which has a thermal time constant of tens of minutes. So we're talking huge orders of magnitude difference between what transients really mean for those different systems. So when you're thinking about transient loading conditions, it's important to think about the duration of those transient conditions in respect of the different parts of the system which then respond to it, because then your management of the thermal design would have to then adapt to whatever those time constants are. So I think that brings us hopefully now to the end of our presentation. I hope that that's been useful and interesting for people to join today, and we'll move on to some questions. Okay, let's take a look. Oh, good. We've got a few questions coming in.
So just first, go to the chat. There were some questions about how to access the previous webinars.
Oh, okay.
I think that people, they have to fill a form and they just receive a link or a password or something. It's just
If you give me a second, I'll put a link up in the.
I posted the link already.
Oh, okay.
Some people were saying that it was not working, but I think it just gives you a form, access to a form. You fill in your details and then you get access after that.
Yeah, that link takes you through to our website. So you have to put your details in there, and then it'll take you through to another page on our website where all of those previous webinars are there. I think at the moment we have webinars 1 to 10. Jose, your webinar you did on Tuesday this week isn't up there yet. I still need to put that up, but it will be there shortly.
Okay, that's fine. I suppose they can send you an email if they have any issues there.
Yeah, exactly. Yeah, please get in touch.
Okay, thanks.
No problem. Thank you. Okay. So first, I'll just start at the top of the questions here. Does the heatsink specification sheet specify the thermal capacitance like 45 joules per Kelvin, like values used for the Plex example? I think that depends on the vendor. Some of the I guess the vendors that are providing really high performance heat sinks will provide that data, or if it's not, you can ask them. For low cost commodity heat sinks, it's pretty hard to get that sort of information, to be honest. You can capture it yourself though. You can. I'm a big advocate of doing tests in the lab whereby you can just put a heat source onto a heat sink and then just put a thermocouple in it and start measuring it, and you can look at the rise time. And from that rise time data, you would be able to extract both the thermal impedance and the capacitance. But some people, I think, suppliers like Fisher Electronics have got some very good data. ABL, I believe, have some good data as well. So yeah, it varies from manufacturer to manufacturer. The next one down, what are the key specs to look out for when buying an infrared camera for electronics, cooling and monitoring? Okay, that's another good question. So we bought ours quite a few years ago now, and it was a fairly high-end camera. It's been very, very reliable. I think the only thing I would potentially want to change about it is you need to think about the size of components you're going to look at. So the one we bought here allows you, if from our presentation today, in fact, if I go back a few slides, where are we? Yeah, if I go back a few slides to the thermal images I showed here. So this is about what you can see on the screen here is about as close as you can get with the particular lens that we have on the front here. If you try and get closer to that to look at the real detail of tiny components, you start to lose the ability to focus. So if you want to look at really tiny components or very small areas, you can on this camera, you can actually buy another lens to put on the front to give you that ability to focus in, a bit like a normal camera. You just need to choose the right sort of lens. So the first thing I think to say is to consider what sort of a size of a thing you want to look at. Is it something really big or is it something really small? Because that will affect your focal lengths and the sort of lenses you might choose for it. The other thing is the number of pixels. The cheaper cameras don't give you as many pixels, although infrared imaging technology has moved on massively since we bought this camera, and the price point has come down significantly. You can get, for less than I think even less than £1,000. I think you can even get an add-on thing for an iPhone now that gives you the ability to do thermography. Really what you're trading off there is the number of pixels and the frame rate, because when you've got a camera like the one we're showing here, you've got, I can't remember the exact pixel, it might be 600 by 800, something like that. And the frame rate is up to 60 frames per second. So if you're trying to capture very fast transient events, you need a fast frame rate to do that. But if you don't really care about that, you don't need a fast frame rate. So it really depends on your application. Let's move on to the next question.
There are some new questions. I think there's one that is quite good at the top now.
Oh, okay. Okay, yeah, let's have a look at that. So what kind of extra attention on thermal management should be paid when we are dealing with those design including SiC-based or GaN-based power devices? I like that question. That's a fantastic one. So this actually alludes back to the slide at the end of my webinar. When you're working with SiC or GaN-based power devices, there's two things that are going on that you're going to find hard from a thermal management perspective. Firstly, the physical die that those parts are being built with is smaller than for a silicon device. So even if you have the same amount of dissipation, you have a challenge with getting the heat out, just because, and Jose talked about this on his presentation on Tuesday. So it's much harder to get the heat out of a very small die, so you have a problem with cooling them. And secondly, coming back to that point about the conflict with EMI, SiC and GaN-based devices, typically their orders of, the dV by dt they're operating at is so much higher than it is for silicon, that the amount of current that you can get pumped parasitically through your insulating layer onto the heatsink is going up massively. So you have to be careful on how you manage your EMI because of that effect. So how you return parasitic currents generated onto heat sinks, you have to pay far more attention to that with these sorts of wide bandgap designs. But it's a real challenge actually for particularly GaN devices. We've found them to be quite hard to keep cool, and there's a lot of work being, again, Jose talked about this in his webinar on Tuesday. Advanced packaging techniques for wide bandgap are starting to address some of those cooling challenges. So it's ultimately it all becomes a big thermal challenge. Let's see what other questions we've got here. So here's a question. So what is the criteria to select the liquid cooling system? And that, again, it's really application dependent. If you're operating in an environment where you're operating down to very, very low temperatures, then you don't really want your cooling fluid to freeze, because then you'll lose cooling and the system can get damaged. So you might want to choose a particular coolant, like a glycol mixture, that has certain characteristics which allow low temperature operation without it becoming too viscous, or at least it has a behavior which is acceptable at the low temperature you're operating at. The other side of it is you also want a material, a liquid that has a high thermal capacity. So you want to be able to put a fair amount of energy into it without causing the temperature to rise. And there are some other things like, the level of contaminants you get in there, and how often you then have to change the liquid coolant and that sort of thing. I think I remember reading about effects whereby, if you've got electric fields that your coolant is subjected to, it can create problems as well. But I'm sort of guessing a little bit on that. But you have to be, it's a very complex science, I think, to choose that particular liquid cooling system, and it's really determined by the application. So let's see, we can move on here.
I think there's an interesting question about the thermal interface. If you scroll down.
Okay.
Just in the example of the liquid cooling cold plate.
Okay, let me just. Oh yeah, in the example of the liquid cooling cold plate of 0.005 degrees C per watt, perhaps thermal interface resistance will add additional resistance. Yes, it would do. So effectively, that 0.005 degrees C per watt would be from the metal of the the cool plate to the inlet temperature. So anytime then you've got your further thermal impedances as you go back up through the stack to the physical junction of that semiconductor, the thermal impedance is going to rise. But what we're saying is that the cold plate itself is going to do a very, very good job at maintaining a nice low temperature, and then really the rest of the thermal behavior of your system is going to be largely determined by your power semiconductor package and its bonding onto that heatsink. That's not the case with a passively, like an air-cooled heatsink or a passively cooled heatsink. the heatsink temperature will rise significantly, whereas liquid cooling, it stays very, very stable when you dump power into it, and that's quite a nice thing for cooling. Okay, there's another great question here. For metalwork around magnetics for cooling, it was recommended to avoid air gaps. How do we quantify if a particular air gap will be significant or not? Maybe I misrepresented that slightly. So you need to avoid metalwork near the air gaps, but most magnetic components, if they're using ferrite, need an air gap. So what we're saying is just don't put the metalwork anywhere near the air gap itself. We, on our earlier webinars talking about magnetics design, we talked about fringing effects near the, if you look at a standard E-core transformer and you put a gap just in the center leg, you get fringing fields going around that gap, and they can start to impinge on the first layer of primary winding and cause loss in that layer. There was a rule of thumb that I don't know how accurate it is, but it's been told to me a few times over the years, that if you can keep your metalwork or your winding a distance of about 3 times the air gap away from the air gap. So if you have a 1 millimeter air gap, you need to keep any metal or winding about 3 millimeters away from it. You should be okay. Now, I don't know whether that would have the same, it should be the same effect for metalwork around transformers as well. So that would be a good starting point. Normally what you would do though in any sort of magnetics like this is you wouldn't really gap the outer legs. You would just gap the inner leg, or use a distributed gap in the inner leg, and then the outer legs don't have any gaps, and you can just use normal metal cooling all the way down them. There's a question here: is a vapor chamber based heat sinks currently cost friendly for a consumer electronics? Yeah, I've heard about these vapor chambers. I've not actually got any practical experience of them, to be honest, so I can't really answer that one. They are, I believe, fairly effective. Whether they're cost effective for consumer, I think if they were, you'd see them being used. You see heat pipes on consumer equipment all the time. Vapor chambers, I've not seen that so much. I can't really comment further on that one, but it's certainly something that maybe we need to put a slide on vapor chambers into our presentation here, actually, because I've read about those in the past, and I think they can be very effective, but I think they're quite expensive. Let's move on. We've got coming up to nearly finishing all the questions, I think.
One on top, one at the bottom.
Yeah, let's do the one at the bottom first. So the ambient temperature will depend on the fan airflow rate, etc. So when we run the first test case or iteration, maybe we need to make a guess. Anytime you're going through the design process, you need to assume an external ambient, that's not normally something that's determined in your spec. So I think nothing really beats real physical tests, and this is why it's important to use thermal chambers as well, because if you use a thermal chamber, you can control that external ambient. What you actually see in the field is going to vary massively. So the important thing is that we end up testing to a specification, and that we provide data to show that the performance of the particular power converter meets the requirements if we meet the ambient requirements that are detailed in the specification. So you need to make a bit of a guess, but I don't think that's necessarily a problem though.
So if I can comment into that, so sometimes when you put things operating outside of an enclosure, things are fine, and then when you put your converter into a small box because you want that compact, suddenly you have heat building up and your ambient temperature is no more 25 degrees, it's 70, 80, and you run into real trouble.
Yeah, that's a very good point. I mean, that again comes back to the whole idea of what actually is ambient, and it depends. It's what is ambient from the perspective of the system you're trying to cool. And like your example there, Jose, that depends on whether you put it in a box or not. So it's really important to consider that. I think the last question here, the liquid cooling tube isolation methods from the switch, the liquid cool. I think this question is about how you electrically isolate the liquid cooling tube from the switching device. This is the Litz wire with that very thin layer of tubing down the middle. So the examples we've seen, and we've spoken to a few manufacturers about this, that's actually a plastic tube that goes down the middle of the winding. And then when the winding comes out, obviously it needs to split with the electrical part going to your electrical circuit, and then the tube goes off to your water cooling circuit. We've not actually built one of those before. I can imagine mechanically, again, it comes back to that comment earlier that as you go up in power and you need to use these more exotic ways of cooling things, your design, as much of your design time is spent on mechanical and thermal issues as it is on electrical. And in this case here, I can imagine there are some interesting mechanical design challenges in implementing that sort of an approach. But if you can make it work, the performance benefits from a thermal design perspective would probably be huge for a transformer, but probably only justified at very high power levels. I think that's all the questions from today. If there's no further questions coming in, I'd like to thank you all very much for joining. I hope it's been a useful presentation today. It's really a high-level overview on thermal design, and there's a lot more to it than obviously what I've presented today. It's probably one of the most important areas of high power electronics is keeping things cool. So it's something that's worth becoming very capable at and very familiar with. So I think with that, I would like to say thank you for joining and hope to see you next time. Thanks very much. Bye-bye.